All right, so to refresh your memory, because you probably weren't thinking about this because it wasn't on the exam, there's this quantity called electronegativity that tells us something about whether or not the atom pulls the electrons toward it in a bond. So we said things like CO make polar bonds because the O has a higher electronegativity and pulls the electrons toward it, whereas the carbon does not have as high of an electronegativity. So what is the difference? Well, there's some basic guidelines that have been decided upon, and they're just guidelines. But generally, if we calculate the difference in the electronegativity, so we subtract one electronegativity from the other, 0 to about 0.4 difference, we call that nonpolar. (0.4 to about 1.8, we call that polar, a polar covalent bond. And then above 1.8, we call that ionic. So rather than thinking of covalent and ionic bonds as totally different things, it's really just different parts of the same spectrum. Things that have a big difference in electronegativity, we call ionic. Things that have less of a difference, we call polar. And things that have basically no difference, we call nonpolar. Now, why do we care about that? Well, we care about this because it affects how molecules interact with each other. So we're going to get into this later, but basically if something is polar, like a CO bond is polar, and we said that it could have a partial negative charge on the oxygen and a partial positive charge on the carbon, that means that other molecules with similar type things can line up with it and can associate with it. So you might imagine another CO bond lining up backwards so that the positives and the negatives line up, and we know positive and negative attract, so this kind of holds the molecules together. So depending on how polar the molecule is, we can say something about how tightly the molecules are going to hold each other together. And that will affect things like boiling points and melting points and volatility, and we'll get into vapor pressure later, all kinds of different good stuff. So it's not enough to just look at the polarity of the bonds. We need to look at the polarity of the whole molecule. And to do that, we need to know the shape of the molecule. So we're going to skip the section of the book that talks about how to figure out the shape of a molecule. You're welcome to read it if you're interested, but we've just decided that wasn't something we're going to do in this class, so it's not in our objectives. So I'm going to give you some shapes of molecules, and I'm going to show you how to calculate the overall polarity based on those shapes that you're given. So let's try that. Let's start with water. Does anybody know what the shape of a water molecule is? What it looks like?
Like Mickey Mouse?
Yeah, like Mickey Mouse. Like this? Is this what you meant by Mickey Mouse?
Yeah.
Yeah. Right. I assume that, yeah. Yeah, so that's right. It's kind of a bent structure. Sometimes it's written up like that. Sometimes it's written down the other way or to the side. Doesn't matter. But it's got this bent structure where the hydrogens are offset from the oxygen. And the that's going to become important, as we'll see in a minute. So how do you determine if we call this whole molecule polar? We talked about how to determine if a bond is polar. You look at the two atoms, you figure out if there's a difference in electronegativity, and if there is, you call it polar, and if there's not, you call it nonpolar. But for a whole molecule, what you have to do is you have to look at all the bonds and then kind of see how they all add up in the whole overall molecule. Let me show you what that looks like in water. Let's just look at each bond individually. So we've got an HO bond. Is that a polar bond? Let's go check. We look at this chart. Is an HO bond polar? What do you think? Yeah? Yeah, how do you know? You're right. But how did you, just a guess? Okay. Anybody have a reason? Yeah.
Would you subtract the 3.5 or subtract 2.1?
Yeah, we look at hydrogen and we look at oxygen, and we say, okay, one has electronegativity of 2.1, one is 3.5. The difference between those is 1.4, right? So that puts us squarely in this polar covalent region right here. So we would call those bonds polar. All right, next question then is, where do the electrons go in a polar OH bond? So the OH bond is polar. Where do the electrons go? Are they pulled more toward the oxygen or more toward the hydrogen? Let me look at those numbers again. Are the electrons going to be pulled more toward the oxygen or the hydrogen? The oxygen? How do you know? You're right. But how do you know? Yeah, because the oxygen has the greater electronegativity, and that's what that is. It means how well it pulls the electrons. So that means that in that bond, the electrons are going to be more around the oxygen than around the hydrogen. So if we look at that molecule and what that means for that molecule, that means that in each bond, there's going to be more negative around the oxygen and more positive around the hydrogen. That electronegativity means that the electrons get pulled to the oxygen and become more negative there. And then it's going to be the same thing on the other side, excuse me, because we've got the same kind of bond. If the other side were some other kind of bond, like an OO bond, it might be different, and there might not be polarity over there. But in this case, we've got the same thing on both sides. So now we can look at this whole molecule overall, and we can say, well, you know, you can imagine a line kind of splitting through the middle, and everything below it is more negative, and everything above it is more positive. All the positive stuff is kind of above, and all the negative stuff is kind of below. So that means that this overall molecule is polar. Yes, it is polar based on what we just found. That there is, what polar really means is positive and negative separation. So can you separate the positive and negative parts of the molecule? And if yes, then we call that polar. If no, then we call that overall nonpolar. Right, let's look at another example. Carbon dioxide. Carbon dioxide looks like this. Has two double bond carbon oxygen. And now we want to decide if it's polar. Now the difference in these two structures is the shape. Of course, well, the atoms also, but the shape. Well, whereas water has that bent Mickey Mouse shape, then carbon dioxide has a straight across linear shape. So let's go back up to our table. Would you expect a CO bond to be polar? Yeah, because you see, again, a difference, a relatively large difference in electronegativity of about 1. So we'd expect that one to be polar. Okay. Which atom pulls the electrons more, the oxygen or the carbon? The oxygen. Yep. So then it means we can do the same kind of thing and say, well, there's going to be some positive over here, some negative over, whoops, wrong way, sorry. Some negative over here and some positive over here. And some negative over here and some positive over here. So once again, we have separation of positive and negative. We have polar bonds within this molecule. But in this case, the overall molecule is not polar. Why do you think that might be? Carbon dioxide is not polar, even though it's made up of polar bonds. Why might that be? Yes. But it is a gas, but water is also a gas, depending on temperature. It has to do with how that structure is laid out and what this would look like in 3 dimensions as an actual molecule. Now, we draw these molecules as these individual letters connected by lines. But what they really look like is just kind of blobs, big electron-type blobs. So water would look something like this. You'd have a big oxygen atom, and then you'd have these 2 kind of hydrogen atoms coming off of it. Oxygen is much bigger. So more like a bear than a Mickey Mouse. I guess it's still sort of Mickey Mouse, is that?
Yeah.
Yeah. But once again, we could see that the positives around the hydrogen are kind of all on this side, and the negatives from the oxygen are all kind of over on this side. Carbon dioxide, because it's straight across like that, is a little bit different. You have this carbon atom in the middle, and then these big oxygen atoms on either side. And so the positive part, the carbon part, is pretty much completely surrounded by negative oxygen part. So how that molecule looks to the outside world, to other molecules, is kind of like all the same. Rather than having an area of positive and an area of negative, carbon dioxide just kind of looks all the same. Another way we could think about that is that these electrons are kind of pulled this way in this bond, but then they're pulled this way in this bond. So overall, they just kind of cancel each other out. And the way you do this more technically, if you really want to calculate what's called a dipole moment, which is the actual quantity of the polarity, is you would take those magnitudes and directions of those vectors and you would add them together. And so you would say that this vector plus this vector gets you back in the middle. It's like if you go 5 miles that way and 5 miles that way, you end up where you started. Yeah.
So just a quick question. What you were saying first about using the values on the periodic table to subtract and get the difference. So that's only determining the polarity of the bonds.
That's right. And then you have to look at
what is this called? Just the polarity of the molecule.
Of the molecule, yeah, the overall polarity. So this one we would say is not polar. We would say carbon dioxide is not polar, even though it's made up of polar bonds. All right, let's look at one more example. We're going to look at 2 very similar compounds, SO2, sulfur dioxide, and SO3, sulfur trioxide. Sulfur dioxide looks like this. And sulfur trioxide looks like this. There's a couple different ways to draw these, but this is one. Now both are made up of the same types of bonds, obviously, SO bonds. So if we want to determine something about the polarity, we first have to see, well, is an SO bond polar in the first place? Before we look up at the table, based on looking at the periodic table, what do you think? Do you think that an SO bond would be polar based on the trends that we know about, or do you think it would not be polar? Why not? They're pretty close together, yeah. So it might be reasonable to think that they're not. But if we look at these numbers, we'll see actually stuff close together can be reasonably different, especially if it's in a different row of the periodic table. So in this case, as we move up, we increase the electronegativity. So oxygen has a considerably larger electronegativity than sulfur. So those are polar bonds. So the first thing we check, is an SO bond polar? Yes, it's polar. Then what can you say about the overall polarity of these molecules? Would you say they're both polar, both nonpolar, one polar, one nonpolar? What do you think? Both polar? Okay. So you can see, you would say, yeah, the SO bonds, we would draw them here. The oxygen is going to pull the electrons away in both cases. And so remember what we're looking at when we look for overall polarity. We're looking for kind of two sides of the molecule. Polarity just means split into two parts, positive and negative. So can you split those molecules into two sides where there's kind of a positive side and a negative side? That's really what we're asking here. What do you think?
The first one you can.
The first one you can, yeah. And that shape is just like water. So, so if we kind of cut through here, we can imagine that that S side of the molecule is positive and the O side is more negative. What about the other one? Not so much? Right, we got the same issue with carbon dioxide. So it's really a question of symmetry. If you have a highly symmetric molecule where it kind of is the same all around, generally that's going to lead to something being nonpolar because you're not going to be able to separate the positive side and the negative side. And then if you have something that's asymmetric, that's not symmetric, you can say, well, this side is positive and this side is negative. And that will usually work out that way. All right, I want you to try one more example. This one's a little different. This is ammonia, which has a formula of NH3. And its shape is a little tough to draw. It's a three-dimensional type shape, so I'm going to do the best I can here. But the nitrogen is kind of in the middle, and then the hydrogens come off in a pyramid-like shape. So in this molecule, you might imagine the shape is called a tetrahedron, or tetrahedral shape. A tetrahedron is a shape with four equal sides and four equal edges and four equal angles. And this is kind of like that shape. So is that molecule overall polar or not? Let's go back and check our NH. So is an NH bond polar? Yeah, it is. So is this molecule overall polar or not? Yeah, it is. And how do you know? Yeah, you can kind of separate the two sides. You can imagine, since it's three-dimensional, we have to look more like at a plane or something. I'm not going to be able to draw this very well, but you can imagine a plane kind of cutting this molecule so that the N is above it and the H's are below it. And so that top part where the N is would be the negative part, and the bottom part where the H's are would be the positive part. So it would be like positive below the plane and negative above that plane. Biology's having a dance party. Though to be fair, they're always having a dance party. So. All right, so you think you can do that? Maybe? Probably? Yeah, you can. One more? All right, let's take one more.
I just have a question, like on a test or something, like how we were provided with the periodic table, would we be given those numbers, like those values of electronegativity?
Depends on the question.
I mean, I guess, is like that something we should like know or memorize?
You should know, yeah, here. So you should know
in general, like
the general directional trend. Yeah. You should know the general directional trend. So you would expect that anything to the right of something else, there would be a polarity difference. Anything above something else, there would be a polarity difference. Okay. That's not always true across the periodic table, but if you just remember that, I wouldn't ask anything weird like in the middle that doesn't fit that.
Okay.
Or if I did, I would give you the numbers. So, yeah. Another molecule. We're going to look at CHCl3, which is a molecule called chloroform. Chloroform has a similar structure to ammonia with this kind of three-dimensional arrangement, pyramidal arrangement. But now it also has this hydrogen coming up off the top. So it's a little more of an asymmetric molecule. So this time without looking at the chart, actually, well, yeah, we should still look at the chart for this one. But well, I'll put it back. So let's just check our chart. We can see that a carbon-hydrogen bond is not really polar. The difference is not big. And a carbon-chlorine bond is just barely polar. So now we're back. Is that better? So a carbon-hydrogen bond is not polar. A carbon-chlorine bond is barely polar. How do you work this out? And how do you decide if this overall molecule is polar or not? Right. Carbon hydrogen is nonpolar.
Did you just not draw the electrons around the CL?
Right. Yeah, there should be electrons around the CL. They didn't. There. All right, so who says chloroform is polar? We're still thinking about it. You guys say it's polar? Yeah, polar. Non-polar? Okay. I guess it's polar then. We'll just go by whatever everybody thinks. Is that how it goes? No. No? Okay. But you're right, it is polar. And just barely, because there's not a big difference between carbon and chlorine, but there's still a little bit of a difference there. So we can say that if we imagine kind of cutting this below the carbon, the chlorine parts on the bottom would be more negative. The carbon-hydrogen part on top would be more positive because, well, there is no difference in the carbon and hydrogen. And so we would see that as just kind of partially positive. But as we saw, there's not a big difference between carbon and chlorine. So chloroform is not a terribly polar molecule. In fact, it's very volatile, which is why it used to be used as an anesthetic because it vaporizes very easily. And now we know it's a carcinogen. We don't use it anymore, but it can still have dangerous vapors. All right, so let's talk about how these things affect the interactions among molecules. We talked about, I mentioned briefly that the polar parts can kind of line up and interact with each other that way. And this can have some effects in physical properties, like one thing the book talks about is melting points. We're going to look at some melting points of different compounds, just a few different ones, and then we'll talk about how we can explain those and how we can predict them on these ideas of polarity. So what's the melting point of water? 0 degrees C. Thank you. Everybody knows that, right? Okay, good. What's the melting point of fluorine gas? You don't have to know that one. No, I just looked it up. It's minus 220 degrees C. So you've got, think about for a minute what that means. Oxygen is a smaller molecule than fluorine, F2. Yet fluorine has a melting point hundreds of degrees colder than water. So we'll think about what that means. What's the melting point of salt, sodium chloride? Have we ever melt salt? It's pretty hard to do. Melting point of salt is 801 degrees C. So you need to get pretty hot. And then hydrogen chloride, this is not hydrochloric acid, which is dissolved in water, but hydrogen chloride gas is minus 115 degrees C. So kind of in the middle of water and F2. So huge differences in melting points, obviously, but these can be explained by the ways that these molecules hold together. These ideas of polarity tell us how tightly molecules can hold each other together. And these attractive forces are called, of course, have a name. They're called intermolecular forces. Which we can think of as attractions between molecules. If you're not familiar with that prefix inter, it means among different ones. The opposite of it is intra. So you could have intermolecular forces or intramolecular forces. Intramolecular forces are what we call bonds. Those are the forces that hold the atoms together inside the actual molecule. So intermolecular forces are the forces that different molecules are held together by. So when we're talking about intermolecular forces, we're not talking about the bonds. We're talking about how do different molecules interact with each other. So there's pretty much two categories of these that we're going to look at. And the first one is called dipole attractions or forces. And this is the name for what we talked about before, where molecules that are polar can attract each other. So if we look at a molecule like HCl, H and Cl have a difference in electronegativity. So we have a partial positive on the hydrogen and a partial negative on the chlorine. Another HCl molecule can then line up with this. So that the positive from the hydrogen lines up with the negative from the chlorine, and they can kind of make a big chain like this. Now, I kind of just drew it as some dots because this isn't a bond. They're not sharing electrons. It's not a covalent bond. It's not nearly as strong as that. But they are attracted to each other because of a little bit difference in positive and negative charge there. So it does exist. It does affect it. That's how we can explain something like HCl having a melting point that is lower than water, but not quite as low as fluorine. Is fluorine F2 polar? If you had FF, would there be a difference in electronegativity? No, because it's the same thing. So the difference would be 0. So that one would be totally nonpolar. And that has a super low melting point, which means the forces that hold those molecules together are not strong. HCl is not quite as low. So that tells you there's something going on in HCl that's different from F2. And that thing that's different is this dipole-dipole attraction. Now that also kind of explains the water, but water has an even higher melting point. And so something special is going on in water. I'm going to call this 1A because it's really a type of dipole-dipole attraction. And it has a terrible name. And that name is hydrogen bonds. And I'm going to put it in quotes. And the reason it's terrible, not that it's like offensive or anything, but it's confusing. Hydrogen bonds makes it sound like it has something to do with hydrogen bonding to something, but that's actually not what it's talking about. It's an intermolecular force, and it's the dipole interactions that you get with NH, OH, or FH bonds. So any molecule that's made up of these bonds can have these extra strong forces. We might call them super dipole attractions. That's not a real term. I just made it up, but it's kind of what we're talking about here. That it's the same type of a force, that these things have these polar attractions. But because nitrogen, oxygen, and fluorine are so electronegative, they're like extra strong. And they hold each other together extra tightly. And so any molecule like water that can have these types of forces is going to have an extra high melting point, extra high boiling point, because the molecules can hold each other together so much more tightly. So far we've talked about the forces in HCl, called those dipole-dipole forces. And in water, we called those hydrogen bonds, which are a type of dipole-dipole force. We also know the type of force in NaCl. We haven't named it because it's not a molecule, but what types of forces hold the Na and the Cl together in NaCl? What might you call those? Nobody? I'm sure you know it. It's ionic. So those things are ions. They're held together by the forces that hold positive and negative things together, which are called electrostatic forces. But those are the ionic forces. And those are much, much, much stronger than any of the stuff that we're talking about between molecules. And that's why something like an ionic compound like sodium chloride would have a much higher melting point, much higher boiling point, because those things are really held together much more tightly. So the last one is we have to talk about fluorine. Now we decided fluorine was nonpolar, and that's fine. But nonpolar molecules still have to interact with each other. So even if they don't have any of these special dipoles, you still can freeze fluorine. So you get it pretty cold, but you can freeze it. So that means there must be some kind of forces going on in there, something holding those things together. And those forces are called dispersion forces. And all things, polar and nonpolar, have dispersion forces. Nonpolar molecules don't have anything else, so they only have these dispersion forces to work with. And they're pretty weak. But that weakness depends on the size of the molecule. So as a molecule gets bigger, the dispersion forces can actually get substantial. And a good example of this is hydrocarbons, molecules made from carbon and hydrogen. We said there was no polarity between carbon and hydrogen, so these are nonpolar molecules. But if they get big enough, they can still be solids. Anybody know what hydrocarbons are as they get bigger? What kind of materials we make out of hydrocarbons, or we use hydrocarbons for? Things that are only made out of carbon and hydrogen. We mostly just burn them. So we use them as fuels for different things. If you have 8 carbon atoms with 18 hydrogens, so C8H18, that's called octane. And that's the major component of gasoline. You might have seen the little number, the octane number that's on the pump. That's the amount of gasoline that's made of that octane molecule. And that's, of course, a liquid. So when that gets big enough, you're talking 8 carbons now, getting a pretty big molecular weight. That is becoming a liquid, and so those forces become stronger. And then if you get really, really big hydrocarbons, you have waxes, which also burn like a candle made out of wax. Those are hydrocarbons also. They're so big that they end up being a solid, so the dispersion forces end up being strong enough to make it into a solid. And so we can fill in our final bit of our table here that F2 would have these dispersion forces or dispersion attractions. So now you can decide whether a molecule has polar bonds in it, then whether the molecule overall is polar or not, and finally we can rank them in their melting and boiling points of how we would expect them to have a higher or lower melting or boiling point. So that's kind of the goal of all of this. You determine what types of forces they have, and then how that would affect the boiling point. Sound good? Exciting? Everybody seems pretty excited. All right. So you can practice that in your homework. Let's start a new thing and get into this next part of the class. Now this is a part that can give people some trouble, so we're going to spend some time on it. And the good news is that once you kind of get it, then it's great. Then it's like every time you see one of these kinds of problems, you're just happy because you know how to do it, and it's always the same. So hopefully we'll all be able to get to that point. And that is talking about something called the mole. Has anybody ever heard of this before? Heard of this? Maybe in some other classes? It's not the little animal, it's something different. So I notice, let's see, 1, 2. There are 13 people here today. Do we have a word for that number?
13.
Yeah.
What are you asking?
Like if you had 13 of something, you could say you had a what of those things? Does anybody know?
Oh, baker's dozen.
A baker's dozen. Has anybody heard that? Yeah. That's because bakers can't count, I guess? I don't know.
No, because they make them themselves.
Oh, is that right?
Yeah.
Okay. Yeah, so did anybody bring donuts? No? All right, we'll have to bring donuts sometime. Get some donuts. I like donuts. But anyway, this is a point to this. So we have these numbers that have words associated with them, like that there's a baker's dozen here, or that we would say, more common one, of course, is 12 items is 1 dozen. Baker's dozen. So if we had 6 people, how many would we say we have in terms of dozens? Half a dozen, right? Like 0.5 dozen or half a dozen. So you can talk about quantities in these kinds of other terms. What other words do you know that fit this?
Like a pair?
A pair, sure. So that would be 2 is 1 pair. Few doesn't really have a specific definition though, right? Could be 3, could be 4. Just means like, so if he said like, hey, can I have a few M&Ms? You would like count out 3.
Give us 3.
Exactly, okay. I've always had a kind of less specific view of few. What do you think? Maybe else? I don't know.
What about couple?
Couple? So that would be 2, like pair, yeah. There's not that many of them. What's 144? That's true, but there's a name for it. Do you know what that is? Yeah, it's a gross. A gross is like a dozen. 12 sets of 12. I don't know. Anyway, there's some words like this. The reason we do this is that this mole is another version of this. It's another name for a certain number of items, and we call it a mole of them. Does anybody know what that number is? It's a big number. So these were all relatively small numbers. The mole is 6.02 times 10 to the 23rd. Its number is so big that we really have to use scientific notation to express it. Because otherwise you're talking about a 6, 0, 2, and then 21 more zeros. That's a really big number. So why would we need a number this big? And why would we need a special name for a number that's this big? Anybody know? What's the point of having a number? Obviously, you're not going to get a mole of donuts that we a lot of donuts.
Donuts.
Yeah. Even a gross of donuts would be kind of gross. Maybe that's where the name comes from. So what do we need this number for? Why have this giant number? What do you think it has anything to do with? Of what?
We use it for concentration and physiology.
Use it for concentration? Okay. In physiology? Yeah. Yeah, because we'll talk about those too, things like molarity right? Yeah, well, you need a big number like this because it helps you go from the small scale to the big scale. So this number is ridiculous when we talk about anything that is in our normal realm, like donuts or pennies or even grains of sand. This number would just be an unimaginable amount of that because it's so big. But if you're talking about something that is almost unimaginably small, then that many of those things brings it into our realm. So the mole is how we kind of convert from the atomic realm, the realm of atoms and molecules and chemicals, to what we can deal with. Where that number comes from is that is exactly the number of carbon atoms in 12.011 grams of carbon. So if you weigh out 12.011 grams of carbon, which is the molecular, the little red number, the mass number there, if you weigh out that much carbon, that's how many carbon atoms you have. Now 12 grams, that's like a reasonable amount. It's like a small handful or something. So we've taken something that is really hard to count, tiny, tiny atoms, and we've brought it into our physical scale, something that we can deal with. And so the thing to remember is 1 mole of anything is this number quantity of those things. Because it's kind of a weird number and something we're not often familiar with, a number set up like this, sometimes we'll think of it in terms of like, what kind of a unit would that be, or what kind of a measurement is that? But it's not a measurement, it's just counting. It's just this many of those things. That's all it is, just like a dozen. So it doesn't really have a unit to it, it's just a number of things. But we're going to use it in this way. So if we'll go back to food, sweet food in general, like jelly beans. You guys know about jelly beans? Okay. Sometimes you go to like a big candy store and they have a giant thing of jelly beans. And if you guess how many jelly beans are in there, you could win all the jelly beans. Has anybody ever won all the jelly beans? Has anybody ever won something in that style of game? No? Not good guessers? M&Ms? Dum-Dums? How many Dum-Dums did you win? Do you remember? Was it a large quantity of Dum-Dums?
It was just maybe a small jug of them.
Okay. Did you eat them all? That's not a great story, but thanks for, at least we had somebody winning something. You must be good at estimating things. The rest of us are, I've never won that either. But anyway, if you had this, let's imagine, you've probably seen this in the toy store, candy store or something. You've got this giant thing of jelly beans, and it says, guess how many jelly beans, and there's, who knows how many thousands and thousands of jelly beans in there. So how do you think they figure out who wins? Do you think that they pay somebody to count the jelly beans in that giant container? Hey, maybe. Wouldn't you love to just be there and be shouting other numbers at them while they're trying to count thousands of jelly beans? But how do you think they figure that out? Weigh it, right? You could weigh it. If you knew how much one jelly bean weighed, you could just weigh the whole thing, divide, you know how much is there. And so that's what we do with atoms and molecules. We can't count atoms and molecules because they're too small and there's too many of them. But we can know how much one of them weighs, and then we can figure out how much the whole thing weighs, and then know how many we have. All right? So the way that we do that is we look at the periodic table. Look at carbon again. We've already said a couple things about these numbers. The atomic number, the blue one, is the protons, and then we said that the red number was an average of isotopes, of isotope masses. But there's another way that we use this bottom number, and this is the mass in grams of 1 mole of atoms. And the name for that is the molar mass. That looks like ink, so I'm going to like circle that. The mass in grams of 1 mole of atoms. So that means that if you want to know how many carbon atoms you have in a sample of carbon, you got a bunch of black carbon powder. You want to know how many atoms are in there. Just like the jelly beans, you can't count the individual atoms. But you can weigh that, and you can say, well, if each carbon weighs 12.011 atomic mass units, if 6.02 times 10 to the 23 of them weigh 12 grams, then I can figure out how much I actually have there. So let's try see what that would look like. We can answer questions like this. How many carbon atoms are in 1 gram of carbon? We know how many are in 12.011 grams of carbon, so we can know how many are in 1 gram. And we can set this up just like the other conversion problems, using this first idea that a mole is equal to 6.02 times 10 to the 23rd of those things. So here's how we would set that up. We could say 1.00 grams of carbon and we could set up a conversion that tells us how many moles, how many grams are in how many moles. We look at the periodic table and we see that there are 12.011 grams in 1 mole of carbon. So grams cancel, and now we have moles. And then we also know how many things, or how many atoms in this case, are in a mole. We can say that there are 6.02 times 10 to the 23rd atoms in 1 mole. And now moles cancel and we have atoms. So we use the molar mass first for that grams, how many grams are in a mole. And then we use that mole number for how many atoms are in that mole. That mole number, by the way, has a name besides just a mole. It's called Avogadro's number. What? It's getting weird?
Yeah.
Well, it's been weird the whole time. So that number we use for how many atoms are in the mole. All right. Yeah, avocado's number tells you how many are in a guacamole, so that's different. All right, so let's look at now how to do a calculation like this when we don't have a calculator that can deal with scientific notation. Because now we're going to be dealing with these big numbers, these 10 to the 23rd numbers, and we need to be able to do this calculation, obviously, on whatever calculators we have. So all you do is you just ignore that scientific notation part and then stick it on at the end. And then we can correct it if we need to correct it. So we'd go 1 for the 1 gram divided by 12.011 times 6.02. That's going to give us, well, 0.501. So 0.5, I just picked 3 digits, whatever you want. And then we tack on that 10 to the 23rd carbon atoms. Now for this class, if you want to leave it like that, that's totally fine. But the traditional way, the standard way to do scientific notation is you always have one number to the left of the decimal point. So another way to write that would be to say 5.01. And since we move the decimal place over 1, we have to change our exponent 1. And that'd be 5.01 times 10 to the 22. Same thing, same number, but official scientific notation, that first one you can't leave like that. But in this class, you can't. So if you don't want to mess with that, don't mess with it. If you have a scientific or graphing calculator, we've talked about this a little bit before, but just to remind you, sometimes they get screwed up with order of operations if you actually type in 6.02 times 10 to the 23rd. Sometimes it'll mess up your arithmetic. So a better way to do it, what? Did somebody say something? Okay. Let me show you on this one. Do you see? No, nothing's happening. There we go. Maybe. We'll get there eventually. All right, there we are. Okay. Oh, that's not great. You sort of see, there's like this weird glare. All right, good enough. On this particular calculator, and on the graphing ones, it has this too. There's this little key that says EE. It's 2 capital E's. If you have a graphing calculator, do you see it there? It's probably above some other number. That is the scientific notation button. So what you would do is go 6.02 EE, and it should put a little tiny E on there, 23. That way you don't have to do the times 10 to the whatever. That just knows that that's what that is. This will also pair that 23 with the previous number, so you won't get screwed up when you're doing a bunch of other stuff on there. If you do the times 10 to the whatever, sometimes that will screw it up. So use the little E if you've got it. If not, you don't need it. Just tack that part on at the end. All right. Anybody have trouble with finding that, doing that? Okay, let's look at some other ways that we will use this. Now, normally when we go through these kinds of ideas, or when we use these types of calculations, it's because we don't care about the number of atoms at all. That actually we often care more just about the masses. And that's going to be important when we look at chemical equations. So this ultimately, the point of this is going to be, how do you know if you want to do a chemical reaction or you want to prepare a solution of a certain amount, how do you know how much you actually need to weigh out to do that? And you're going to need to use these ideas about moles to do that. All right, so let's do some other versions of this type of calculation. So what if I wanted to know something like this? We need 2.5 moles. The abbreviation for moles, by the way, is MOL. Not a great abbreviation. You save a letter. But M is meters and MO is months, so that's all we got. So we need 2.5 moles of iron 2 sulfate. How many grams is that? 2.5 moles of iron 2 sulfate. That's what we need for our reaction, but we're going to weigh out the iron sulfate on a balance because we can't count individual formula units of that. So we're going to weigh it. So we have to figure that out. Now, iron 2 sulfate is not carbon. There's no entry on the periodic table for iron 2 sulfate. So how do you think we figured this out? Yeah, you can add them all up. So first we need the formula. What's the formula for iron 2 sulfate? Can you get it?
Isn't it Fe2SO4?
Close. Yeah, real close. It's FeSO4. Because iron 2 means iron plus 2, and sulfate is a -2 ion, so +2 -2, they balance out. That's iron sulfate, iron 2 sulfate. So back to the naming stuff from before. If you haven't gotten that yet, please keep working on it because it'll keep coming up. If we didn't get the right formula for that, we won't be able to figure out the right mass either. So we got to get the formula first. All right, so now to figure out this, how many grams are in a mole, on the periodic table for the individual elements, we can just look at that number. If we have a compound like this, we have to add them all up. So we would look up the Fe, which is 50, we'll just stick with whole numbers for now. So we'll say 56. The S is 32. And O is 16, and we need 4 of them because there's 4 oxygens in that formula. So it's 16 times 4. So that's 56 plus 32 plus 4 16s. 152, what you got? We would say 152 grams per mole, which means that there are 152 grams in 1 mole of iron sulfate, iron 2 sulfate. If we weighed out 152 grams, we'd have 6.02 times 10 to the 23rd iron sulfates. But also, we'd have that many, so we'd have 1 mole of them. That's what that number tells us. Now, we're not done with this problem yet, because that tells us how many grams are in 1 mole, and we need 2.5 moles. So now we just have to convert our units the way we've done it before. We can say 2.5 moles, and this time it's really important, let's keep our units straight. So it's not just moles, it's moles of iron sulfate. And when we get into the reaction calculations, it's going to be really important that we know which compound we're talking about. So if we get into good habits of always labeling those units, that's helpful. Also, like on the exams, when I grade your exams, I'm looking to try to give you as many points as possible for every question. So whatever you have on there that could possibly be construed as somewhat right, I want to give you points for that. The more clearly you label your units and you set up your problem and it's like pretty clear what's going on in there, the more I can do that. And so it's like there are several places where somebody might have gotten almost all the points on one of those questions because I could see that you had the whole thing set up right and like you missed one calculation somewhere because you probably typed in a wrong number on your calculator. But if it's all set up, I can see that and I know you basically got it right. If all I see are some like random scattered numbers around and then one with a big square around it that's the answer, if that answer is wrong, I don't really know where that came from and if you were on the right track or not, so I can't really give you partial credit for that. So it's always a good idea to keep things clear, label units, all that good stuff. All right, so we got 2.5 moles of iron sulfate. And we want to know how many grams we need per mole. And that's what that molar mass tells us. So this tells us we need 152 grams per mole. And that gets us to 380 grams of iron sulfate. So just like those other questions, it's the same kind of procedure. We started with moles, we canceled moles so we could get grams. If you think about it that way, the only new thing is calculating these molar masses by adding up the weights. Let's try one going the other way and see if you can do one. How many moles are in 5 grams of, let's say, what's your favorite compound? Calcium iodide. Since you might not have periodic tables with you, what's the symbol for calcium? Ca, that's number 20. And what's iodide? I, yeah. So how many moles are in 5 grams of calcium iodide? See if you can figure this one out. You got to get the formula for calcium iodide and then set up a molar mass type conversion just like we just did. Just so we're not too stuck. Did anybody come up with that formula for calcium iodide? What would that formula be?
Is it CAI2?
Yeah, it's CAI2. The way we get that is we know calcium is +2, it's in column 2A. Loses 2 valence electrons. We know iodide is -1 in those halogens. So you need 2 of the -1s to go with the +2. It's CAI2. Did anybody get a molar mass for calcium iodide yet? How many grams in a mole? What? 294? That seems high. Oh wait, no, it doesn't. You're right. No, yeah. I was thinking something else. Yeah, 294 grams per mole. So let's figure out how many moles are in 5 grams. Now we've got all the information we need. We want to go grams to moles. So to go grams to moles, we need grams on the bottom, moles on top. So that's 294 grams in 1 mole. So that's 0.017 moles. Grams cancel with grams, and we're left with moles. I think that's the number one mistake that people make in these problems is flipping that. So multiplying by 294 instead of dividing by 294. If you follow the units and you think, all right, I'm starting with grams, I need to cancel grams and end up with moles, or I'm starting with moles, I need to cancel moles and end up with grams, you're always going to keep that straight. That's a much better way to do it than just trying to remember, okay, for this problem I multiply, for this problem I divide. As you practice more and more of these in the homework, you'll get better at it, you'll get used to it also. So again, even if you kind of understand this, you definitely want to practice just to make sure that you can do it every time. All right. So the next part we're going to talk about is chemical equations. And then we'll put those calculations in with the chemical equations and do the whole thing probably next week. I just realized I don't think this is saved. Chemical equation is a way of expressing a chemical reaction on paper. And you've probably seen these kinds of things before. It's like something plus something, and then an arrow, and then something else. See something like that before? So it looks like this. I'll give you an example. That's an example of a chemical equation. Let's look at the different parts. So first, we've got this part on the left of the arrow, which are the things that you start with. So what things are combining to do this chemical reaction? In this case, it's hydrogen and oxygen. And so we call these the reactants, or sometimes the starting materials, or sometimes reagents. All kinds of means the same thing. And then on the other side, we've got, what do you think this one's called? Product or products, yeah. What you make. So your reactants, what you start with, products, what you make. Okay, other things, what's going on here? What does this little G mean in parentheses next to the molecule formula? You know what that means? Okay, that's fine. Okay. This is the state. Yeah, so G is for gas. L is for liquid. S is for solid. And then there's one more that we see, AQ, which stands for aqueous, which means dissolved in water. Yeah. So if you see something like NaCl parentheses AQ, that means it's not solid salt, it's salt water, salt that's been dissolved in water. And we'll see some of those. All right, so that's all the different parts of a chemical equation. You've got your reactants on one side of the arrow, the product on the other side, you've got molecular formulas, and then you've got your state. But there's a problem with what I've written right here. This is talking about hydrogen and oxygen gas combining to make water. What's the problem?
We use H2 and O2, but then H2 and then O.
Yeah, we've lost O somewhere in that process. Do you see that? On the left side, there's 2 hydrogen atoms and 2 oxygen atoms, but on the right side, there's 2 hydrogen atoms and just 1 oxygen atom. That's a problem because it violates something called the law of the conservation of mass, which says that mass can't be created or destroyed in a chemical reaction. If you do a chemical reaction between hydrogen and oxygen, an oxygen atom can't just magically cease to exist at the end of that reaction. That's not going to happen. Chemical reactions happen because atoms reorganize and connect in different ways. They don't just magically disappear or appear. So it's a problem. And if we imagine this in terms of what the structures look like, we'd have a hydrogen molecule and an oxygen molecule making a water molecule. And there you can see that oxygen atom kind of disappearing. So we need to fix this. And to fix this is something called balancing the equation. We need to have a balanced chemical equation, which means there's as many atoms on the left as there are on the right. So how can we do that? Can we just put a little 2 here and say it doesn't make H2O, it makes H2O2? What's wrong with that?
It's not water.
Yeah, that's not water anymore, right? What is H2O2? Hydrogen peroxide. Is that the same as water? Not so much. Yeah. Hopefully, yeah, don't drink hydrogen peroxide. So H2O2, so that doesn't work. We didn't make H2O2, we made H2O. So how can we bring this into balance? How do we get more oxygen in here? What's really happening? Any idea?
Is it also creating just oxygen by itself?
So that would be the other possibility. Is there just some more oxygen over here that's being created? That would work. Is that a way to bring it into balance? That would work, but there's a problem here in that that's not actually what happens. So that would be a different process. If we made oxygen atoms, we would be able to see that there were more oxygen atoms coming out or detect them. And that's not what happens. We're only making water. So what this really tells us is that this is the correct process, but this is not the proportion by which these reactants react. So what if instead of doing it this way, what if we react 2 hydrogen molecules with 1 oxygen molecule, and we make 2 water molecules? Does that work? We still have the same things reacting. We still have the same product being made, but we've just made it in different proportions. And now all the atoms are taken care of. We've got 4 hydrogen atoms on the left, 4 on the right, 2 oxygens on the left, 2 oxygens on the right. So that's balanced. How we express that in the equation is by putting a big number off to the left of each thing that's being changed. So we're going to say 2 H2 molecules react with 1 O2 molecule to form 2 water molecules. And that would be our balanced equation. Okay, see? Yeah, there you go. All right. So let's look at how we do this kind of systematically when it gets, rather than just kind of looking at it and trying to figure out, oh, how many of these do I need or how many of these do I need? So let's do another reaction and kind of work through it carefully. We're going to have some iron 3 sulfide solid reacting with some hydrochloric acid. Now, hydrochloric acid is an aqueous solution of HCl. HCl, hydrogen chloride, is gas. And when you dissolve it in water, you get hydrochloric acid. So if we're talking about hydrochloric acid, that's HCl in aqueous solution. And the product from that is a solution of iron 3 chloride and some hydrogen sulfide gas. Now, when you write down equations, if I give you a problem where it says write the chemical equation for this, generally you won't be able to write the states. In other words, whether it's solid or aqueous, if it doesn't tell you, there's no magic way of figuring that out. Except for some of the ones you might know, like oxygen is probably a gas. But you can't really figure that out. So that's usually given to you. You should be able to write the formulas from the names. But the first question we always have to ask ourselves when we write down a chemical equation is this balanced? And when you have a more complicated one like this, it helps to take a little inventory of each side and figure out how many of each type of atom you have. So let's do that. In this one, I've got 2 Fe's, 3 S, 1 H, and 1 Cl. Agree? You see where I got those numbers from? That's how many of each of those atoms I have. On the other side, I've got 1 Fe, 1 S, 2 H, and 3 Cl. I kept them in the same order just so I can clearly compare. And so you can see here that this is clearly not balanced, right? Every single atom is out of balance. That's not going to work. So we have to figure out how to balance it. We balance it by changing that number out front, and then to bring one of the atoms into balance, and then correct our inventory and kind of keep going step by step. There's a little bit of trial and error involved here. So sometimes we'll get something wrong and we'll have to go back and fix it. Let's take a look at that. So it doesn't matter where you start. We'll start with the Fe because I put that one on top, unless somebody has a strong preference of another one. Okay, so we got 2 Fe's on the left and 1 on the right. How would we end up, how can we make them equal? Yeah, we need the one on the right to be 2 instead of 1. But whenever you put that 2 in front, you change everything in that molecule. So you've got to correct your inventory underneath. So now that brings us to 2 of these, but it also changes us from 3 of these to 6. Because now we've got 2 of those whole units, and each of those units has 3. So that's 6 total. It's really important to correct all the ones that change. Otherwise, it's not going to be in balance properly when we get to the end. Now, I kind of like to go with whatever I just changed, then fix that one, and kind of keep going that way. It doesn't really matter. You could go back and do H's next or S's next. But I like okay, we've got the Fe's in balance. Let's go to the Cl's because we just messed with that one. So we got 6 on the right, 1 on the left. How can we bring those into balance? Yeah, we need 6 on the left. So we're going to put a 6 here. And that's going to bring this one to 6. But it's also going to change the hydrogen from 1 to 6. All right. So now we can balance it on the other side. How do we balance the H's out on the right? Right, we need to put a 3 here because 3 times 2 is 6. So now that's going to give us 6 of these, but it also changes our sulfur to 3. And now it's balanced, right? Now it all works. So that's our balanced equation. The reason this is so important is when we start looking at the actual quantities of how much of this we need versus how much of this we need them to be added in the correct ratio. So we know now that if we want to react iron sulfide with hydrochloric acid, we need 6 times as many moles of HCl as we have of Fe2S3. Before we balanced it, we didn't know that. We thought maybe it was just 1 to 1. Now we know it's 1 to 6. And we'll see later that we can also use this to figure out how much of the products we expect to get. So we can calculate our expected yield of the reaction, how much we're going to get from the reaction. All right, let's try another one, and then we'll call it a night. And let's see what happens when it gets a little bit weirder. This is a reaction for the combustion of butane, the same kind of gas that's in a lighter. Combustion is when something reacts with oxygen to produce carbon dioxide and water. See if you can balance that reaction. Do the same procedure. You're going to write down how many of each type of atom you have, and then keep stepping back and forth until you can bring them into balance. You'll also probably find that you'll run into a little problem with this one. See if you can figure out how to get around that problem when you get there. got it? You seem pretty proud of that. Good job. Anybody run into the problem here?
Yeah.
Or it doesn't work? What do you have if that's not working?
I figured it out.
Okay. How'd you figure it out? Or what'd you have to do?
Well.
Okay, we'll step through it and then we'll see what happens here. So I've got 4C, 10H2O. So you got something like that? All right, I'm going to do my card. Now this one, there is one rule about what you should do first. And that rule is if an atom appears in multiple molecules on the same side, save it to last. So in that case, in this case, it's oxygen. Because we have 2 on the left and 3 on the right. Not only is there not a great way to bring those into balance, but there are 2 different things we can change on the right. So if there's multiple things you can change, save that till the end. They'll usually work out at the end. So we can start with either C or H, it doesn't matter. Let's just not start with O because it's in 2 of the molecules. So if we got 4 on the left and 1 on the right for carbon, we can put a 4 here. And that's going to change that to 4. And that's going to change this one to 9. Then we can do, the oxygens won't quite work out, right? So we can kind of save those to last. Let's do our hydrogen. 10 on the left, 2 on the right. So putting a 5 here is going to give us 10 of these. And now instead of 9, we have 13. And now we got a problem, right? What's the problem? Yeah, we only have O2 on the left, but we have an odd number on the right. And no matter how many O2s we get, we can never get an odd number. So how'd you figure it out? How'd you fix it? Anybody figure it out? It's not wrong. We're just kind of stuck, but how can we unstick? This happens a lot when you get kind of a situation where you have an odd number on one side and even on the others, or you have like only multiples of 3 on one side, and it doesn't quite work out. You got to change everything. It means you got to double everything or change everything. In this case, if we double everything, we'll get rid of those odd numbers, right? Because you double something, you get rid of odd numbers. So we're going to go across the board 2. Instead of 4, we're going to go 8. And instead of 5, we're going to go 10. And then we'll do a whole new inventory and make sure everything still matches up. Now we've got 8, 20, and over here, 8, still 20. And now instead of 13 oxygens, we're going to have 26. Right? 16 and 10 is 26. 2 times 13 is 26. So now we can bring it into balance. Let me get rid of these crossed out ones to make it clearer. So we've got a balanced equation now. 2 butanes, 13 oxygens yields 8 carbon dioxides and 10 water molecules. All right, good job. So just like anything else, this takes practice. Go through the homework and balance a lot of these. Once you get the procedure, there's nothing super crazy about it. It's just something you get used to. It's always the same. But once you get used to it, it should be pretty quick. So happy homeworking. And then next week, we will get into the math part of this, of how to calculate the moles in the context of a reaction. So Lab Wednesday, we're going to be analyzing for some cations and anions. Read this one pretty carefully because there's a lot of different parts and they kind of relate to each other. So make sure you know what you're doing when you come in on Wednesday, please. I didn't get a chance to put all your labs in the computer, so they're graded. I'll put them in the computer probably tomorrow, and then you can have them back on Wednesday. Unless I can get them tomorrow.